Cool. Yeah, thank you. Yeah, my name's Eugene and I'm from the database group. So I work with Sam, Adam, and Mike here at MIT. And today I'll just talk about a couple of projects near the end of my PhD to help close the loop on data analysis. And I guess since this is a job talk, I'll start by talking a little bit about how I approach database research and how I view it. And so the way I see it is there's kind of three layers to database research. At the top are applications that make use of database technologies and techniques to just make cool applications, right? And on top of that, then trying to understand what these applications are and how structured data is being used. Lower on is the traditional core database problems, such as transaction processing, like durability, scalability, indexing, partitioning techniques to just make SQL run faster. And then finally, there's extensions at the bottom to provide additional functionality to database systems. And the reason I see it like this is because different applications will necessarily require different solutions at different parts of this stack. And so some of the projects I've been lucky to work on include the web tables project, where we analyzed and scraped over 150 million structured HTML tables on the internet to try to understand what are the structured properties of data on the web. And so one of the things I found while running my scraper in the crawler is this thing, which completely broke the parser that I wrote. So I was sitting there thinking, well, why is there an image when we're looking for HTML tables? And the answer is that this is indeed an HTML table, and each pixel is being encoded as an HTML cell. Right? So I think the lesson that we can take away from this is you can not really trust the internet for anything. And if you do, then things will go very disastrously. So in core database management, I primarily focus on indexing and partitioning techniques for different types of query workloads, like, for example, skewed or time-varying query workloads, as well as car trajectory data. So you can imagine in Boston, we track the trajectories of cabs around Boston as they pick up and drop off customers. And so you can imagine this system allows users to efficiently ask questions such as, well, what was the average car speed in central Boston at 4 p.m. last week? And how do we build the indices and partitioning techniques to do this quickly? And in most of my work, I've primarily focused on extensions to database management systems, including support for fine-grained lineage, being able to ask, well, I want to understand what were the inputs that generate a particular output result. And later in this talk, I'll discuss how we build such systems. Adam Marcus is a collaborator, and I built one of the first crowdsourced database systems. And so this is a system where it can go out and ask humans to answer queries that the database cannot. And I also built one of the earlier high-performance complex event processing systems. And so these are systems to detect complex patterns in event streams, such as stock tickers or sensor events. And so in this talk, I'll focus on two systems that I built for outlier explanation and fine-grained lineage to help close the loop. And these are projects I've built based on an observation about big data, and that it's becoming more than just scalability and high performance, and also increasingly about the people, such as nonprofits, news organizations, and even individuals that want to work with data and make sense of the information they have. And in contrast to these large companies, they can't afford to hire data scientists and these kind of very expensive analysts. And if you talk to these people, their difficulty isn't that Postgres or MySQL isn't running fast enough. It's in other parts of the analysis pipeline. And one analysis that I'll show you that current data processing systems can't handle is simply, you can see this in the medical domain. So there was a 2009 study by the American Journal of Medicine that found that over 60% of US bankruptcies are due to high medical bills. And so let's just see how Jim Michelson at the Mass General Hospital was trying to analyze this. So he collected one of the world's largest cancer databases, right? So this includes information about genomic information, billing costs, and so on. And one of the first things he found that was very surprising is that among all the cancers, lung cancer was costing a hospital an extraordinarily a huge amount of money. And so to give you a sense, if the 90th percentile cohort of these lung cancer patients cost the same as the median, then that would save the hospital tens of millions of dollars. And there's not that many lung cancer patients going to MGH to begin with. And so their team looked into why this is the case. They thought, well, was it because of the stage of cancer? Maybe sicker patients just cost more because they need more expensive treatments. It turns out that's not the case. Then they asked, well, is it a demographic reason? Is it because of lifestyle or because of age or because of income status? No, it wasn't because of that either. In fact, spending more money doesn't even help lung cancer patients survive any longer. Ultimately, they found it was due to a small number of oncologists that were simply overprescribing expensive chemo and radiation and surgical treatments, thinking that it would help the patients when in fact it was just costing a hospital a lot of money. So the reason why I'm telling you all of this is because Jim Michelson is an example of a real data analyst, right? So he has this data and he's trying to make sense of it. However, he's just a domain expert, right? He's not trained in like database systems and data analysis traditionally the way we computer scientists think of it. And for him, building more scalable, more consistent, more durable data processing systems doesn't help him because his problems are in other parts of the pipeline. For example, he needs help building cleaning and import data tools in order to just get his data into a processing system. So for example, one of the problems he has is he's gathering data from multiple sources. How does he connect one patient from one data source with the same in another data source? As he's getting a lot of malformed and anonymous structured data, how does he actually get it into the data management system? And so one of the systems I built is this tool called dbtruck. And the idea is you just give it some structured data. It can be however big as you want. And it robustly tries to figure out, well, what is the schema? What are the columns and data types in the data? And then try to robustly get it into the data management system. And while it's still dealing with malformed records and bad formatting. He needs us to build better visual tools so that he can interact with the data through visual interfaces rather than by writing raw SQL queries in R scripts. But I think most importantly, and what I'm talking about in this part of the talk, is just building tools to help him understand the results. Why were these lung cancer patients so expensive? And so my current research interests are building these types of tools and developing techniques for these non-database experts to help understand, analyze their data. And to this end, I'll talk about two systems I built in the latter part of my PhD, Scorpion and Sub-Zero, that help close this loop from the results back to the inputs. And I'll start by talking about Scorpion, which is an outlier explanation tool. And so one form of outlier we've seen are these lung cancer costs, right? And other forms of outliers you can see from other types of cost analysis, other types of survey and polling data, or even just cleaning your data. And so in this part of the talk, I'll describe Scorpion in the context of cleaning sensor data. And as we all know, sensors are becoming ubiquitous in our lives. So buildings and public infrastructure are all being instrumented to gather and generate sensor information. However, if we want to make use of it, we need to clean it first in order to build accurate models or make predictions. So here, 54 sensors were installed in the Intel Berkeley Research Lab across the entire floor in order as a test bed to gather this environmental information. And so this is a floor plan, and each of these dots corresponds with one sensor that's generating light, voltage, humidity, temperature readings once per minute. So across the entire floor, per hour, it's generating about 3,000 readings. So let's just look at what the average temperature looks like across 2 weeks. Each dot here is the average temperature for 1 hour of readings across the floor. And so you can see that there's oscillations as you would expect because it gets hotter, it gets hotter during noon, and then the temperature drops at night. So there's kind of daily oscillations. However, there's something weird going on here, and so we just plotted the standard deviation as well. And you can see now there's something strange going on in these hours that makes the standard deviation jump up as compared with what we would expect the trend to look like, right? So we would expect the trend to be fluctuating, relatively smallly.
Wait, I'm sorry, the standard deviation of the entire data set?
Yeah, so standard deviation of this point is the standard deviation of all the readings within an hour from all these sensors. Right? So at the aggregate level, this is what you would first look at if you're trying to just get an overview of the data. And so if we can understand, well, what were the sensor readings and kind of describe their attributes that are causing these outliers, then that can better help us clean the data we have and build filters for future data.
So I don't quite understand. So the standard deviation is the measure. So you're measuring the standard deviation of the data up to that point in time?
Oh, sorry, no.
Why does it jump up when the data is actually going?
So the standard deviation of this dot means we gather all of the temperature readings within that hour from all the sensors, and then compute the standard deviation of the temperature.
So is this normalized in some way?
No, this is
Oh,
just the standard.
you're saying, you're just saying that the temperature, the readings varied a lot across all the sensors at
That's
that
right.
time?
That's
Okay.
right. So you see a lot of disparity
Oh, I
during
see.
these hours, and then you don't in these hours.
Gotcha.
Presumably everything to the right is noise. Like
So here
the
is
large
noise.
standard deviation to the right are some kind of noise, whereas the left are sort of normal signal fluctuations.
So no, so presumably there's some noise in the data, and we'd like to understand where it
So
is.
it's a deviation, it's the variation across space, not variation across time.
That is correct. That's correct.
Is
Yes.
it because the temperature is really different, or it's because that you have some errors when the sensor is marginally dense?
So we'll see this. We'll see this. So let me show you a demo of how this works. So what I'm showing you here is this exact same data set, right? And to compute it, we basically group the data by hour and compute the average and standard deviation. And so similar to in the presentation, we can just highlight some examples of what we consider, bad anomalous standard deviation, and then also select some examples of normal ones, and then submit this to Scorpion, the system. And what Scorpion is doing under the covers is it's loading all of the input sensor readings that generate each of these points into memory, and then generating and testing a huge number of hypotheses to try to identify, well, like what is a description of the sensor readings that would be causing these outliers, right, as opposed to these. And so later on in the talk, I'll tell you why this is a difficult problem, but then we should be getting some examples of descriptions. So here, what we're showing is just a list of predicates that the system has generated, right? So what this says is, well, we can blame these outliers mostly on sensor 18 sensor readings. So there's 54 sensors, and we've identified that sensor 18 may be the culprit. And what this means is when we hover over this, we remove sensor 18's readings from the original query and then regenerate the results. And so the scaling has changed, but when we stop hovering over this, we can see that this was what originally it looked like, and this is what happens when we remove sensor 18's readings. And so we've learned something about what are the properties of the noise in the data, and we can either look into it or just further clean the data. Okay, so what are some other examples of questions that Scorpion might be able to answer?
Sorry, I'll agree. What was that C parameter?
I'll tell you later.
Okay.
Yeah.
Fine.
So other questions that Scorpion can answer that we've tried it on Obama's campaign expense data, right? So here, each point is the total expenditure of his campaign for a given day. And when you ask, well, why did Obama's campaign spend millions upon millions of dollars here, the system will generate and tell you, well, if you discount all of the media purchases from his campaign, then that would, so if you remove all of them, then his campaign expenditure would look normal compared to the other days, right? And other examples that we could potentially answer would be, well, why does one school district test better than another school district? And Scorpion might say, well, it's because of the single, child, like 1% families that are really boosting out this district's test scores. And we can really blame it on those families. So to go into Scorpion, I'd like to first give you some background in terms of what the existing work is and why this problem is difficult. And for this, we'll use a simplified version of the sensor data with 5 attributes. So the time, 11 o'clock, 12, 1. Sensor readings 1, 2, and 3, and they're generating just one temperature reading per hour. Okay? And so here I'm just plotting temperature versus time, and then I've highlighted in red the 2 anomalous readings that are at 180 degrees. Okay? And so classic anomaly explanation has been well studied. And what it says is, if I want to understand what attributes of the data are most correlated with these two, it's relatively straightforward, right? We would go to the visualization, highlight these two directly, and then look for their input records and label them as bad. We would do the same with the normal outputs, and then apply any kind of rule-based learning algorithm like a decision tree in order to construct a separator. In this case, something like voltage is less than 2.5 and sensor equals 3 would then match what we consider as the outliers. The problem in data analysis is that we first aggregate the data in order to reduce it to a size that we can either visualize or read. So in this case, we're grouping the data by time and computing the average temperatures. So for instance, this bar is the average temperature of these 3 sensor readings. In this case, when we apply the same technique of highlighting the outputs, these visual outputs, and then labeling their inputs, then we're labeling a mixture of the normal readings as well as the 2 anomalous ones. And you can see how this would then confound the learner into generating a predicate such as voltage is greater than 2.67, which is exactly what we don't care about, right? So this is an example of one class of existing work of rule-based learning algorithms, where they depend on some curated or clean training data in order to construct these classifiers. And in our case, we don't have this kind of data because we're dealing with aggregation results. Another area of research is kind of anomaly detection, right? So this is where we detect anomalies.
Sorry, you're aggregating stuff as you import it into a database?
Sorry, when we say aggregate, what we mean is the user is specifying or labeling data.
No, I understand the query. I'm just wondering why would the user, why is the user not vetting the data going into the database? If he knows that temperature 100 is an anomalous.
Oh, because early on, before looking at the data, he doesn't know this. And when he looks at it, he's looking at aggregated results. For example, in Dr. Michelson's case, they're just getting data from different sources. And they're just trying to get it into some form to put into the database, in which case they can then run these types of aggregation queries to look at the data. But at that point, it's too late. So you can imagine using Scorpion
so now
to...
your user has to know when the result of an aggregation query itself is anomalous, and then sort of backtrack.
That's right.
So how does he know that, because now the data's been processed, right? It's been aggregated.
That's right.
So, and he's doing some sort of hypothesis test, right? This is some sort of, or EDA, right? He's doing one of these two things.
That's right.
So how does he know that the aggregate result is bogus?
So he doesn't know, which is why he just has this hypothesis that, well, I'd like to understand why these look like outliers to me, right? In Scorpion, they say, well, these are the reasons, and then he'll look into those and realize, okay, that's actually fine, and so I can discount it as a real outlier. So this is basically a tool to help you kind of, once you've identified, there's something weird going on with my results, to then try to backtrack and understand why. And then once you understand why, then you can make the decision whether or not this is a true anomaly, or if this is something that you can then add to your model to discount in the future, right? But in order to get to that step, we still need to first go back from the aggregated results back to some description. Is that okay? So anomaly detection helps us find these anomalies, but then we can then use Scorpion to then explain them. And then, of course, there's a lot of work in the database community along these lines. And so I'll just describe them in terms of the types of questions that they're able to answer. So the first one, view condition causality, says, well, I have an input data set, and I compute a bunch of Boolean expressions with them. So for example, the outputs might be true and true. The user then says, well, the first result should have actually been false. So what subset of my data can I munge in some way to cause that output to be correct? Okay? In the how-to work, the user will say, well, the average temperature should have been 20% higher, and what subset of my data can I change in some way to cause this constraint to be true? For example, I could go to one of my sensor readings and then bump its temperature up by 500 degrees in order to boost the average temperature up, right? And then the why not work is also pretty interesting. It says, I expected a record to exist in my result set, and it doesn't. So then, how can I munge either the query I ran or the data in some way to cause it to appear? And so in all of these cases, you can see, the underlying kind of thing they're doing is they want to identify an arbitrary subset of the data, right? And in contrast, what we're interested in, because we want to construct descriptions, is we want correlated subsets of the input data, so that we can then construct predicates around them to create descriptions.
Well, so I like the idea of working backwards, but I guess the alternative is to have sort of plausibility filters on the input side. So, I know I'm looking at sensors, and sensors sometimes go bad, and one mode in which they go bad, and the easiest one is they go bad and they stay bad, for example. So right. I might look for individual sensors that, so I'll just put a thing at the front saying, I'm not recommending this, I'm just saying that I think would be the alternative, right? I put a thing at the front, I'll have a bunch of things that I know could go wrong here for this kind of data, and I'll have a library of, like sensor bug data.
So that's exactly right. And so you can imagine this is the tool to tell you, okay, this is the filter we should apply. And in fact, it turns out that in a lot of cases, it depends on other attributes such as time. For example, in some of the sensor data, you see the standard deviation shoot up. For example, on the left side, the standard deviation kind of shot up a little bit because one sensor was next to the window, and it was just burning up during the noontime, right? And so that's location specific. And so other examples, such as when the voltage goes down, then that's because the battery is dying, in which case such a method makes sense. So this predicate space is huge compared to just arbitrary subsets of the data, right? Because so when I say predicate, I mean a conjunction of discrete subsets of discrete attributes and then continuous ranges over the continuous attributes. And so this is exponential, as we know in.
Another dumb question. So the model here, so the data is being modified or made incorrect in some way, or at least there are outliers in some way. Is the failure model here essentially random independent failure, or could there be collusion? I mean, basically, how nasty could the modifier of the data be in this system and still be able to help me find
Yes. So I'll talk a little bit later about the assumptions that we have.
Okay.
And so one of the assumptions is, well, we can indeed capture this as a conjunctive predicate, right? Yeah. And so the predicate space, as we know, is exponential in the dimensionality of the data, and it's also exponential for the number of the cardinality of discrete attributes, right? If I have 50 sensors, there's 2 to 50 possible clauses over that attribute. And finally, it's also quadratic in the number of unique values for the continuous attributes. And so all of these kind of combined together make this a particularly nasty problem. And so the goal in our work is to figure out, how can we quantify the amount of blame we want to place on a particular predicate as some numerical scoring function. We'd like to develop a general framework that works for arbitrary numerical aggregation operators, and then identify, optimizations for operators that we care about. And underlying all of this, the key assumption is, by deleting those blamed, input records, that will fix the outlier results value, right? So there's other notions of kind of noise, such as, well, I need to perturb my values in some way, but here we just focus on deleting the values. Okay. So then I'll now go into problem 4.
So you decide to delete this 1 hour over which I have averaged everybody's temperature, the 52 sensors.
Mm-hmm.
I'm just going to delete that hour's readings altogether.
No,
Is that what you do?
I would
You
delete
Or
subsets
you
of
go
them.
and disaggregate that hour into 52 readings, and then you delete a couple individuals and you leave the rest?
Yeah, so basically what I mean by this is, well, each average temperature in the previous plot was over 3,000 readings, right, over the entire hour. And so we'd like to identify what subset can we describe that we can delete, right? So we're not going to, if we delete all of the data, then we don't have anything left. So we want to delete some subset and describe that subset. So and I'll walk you through examples of how this works. Okay.
I'm sorry, this is also hard to understand what's going on. So you can actually capture the outliers if we're looking just one of the outliers, right? You can capture the outliers very easily.
If you look at the output.
Yeah, just you have one value, and then you can capture these records out of these 1 million are the outliers.
So
that's very easy to do.
So it depends on the aggregation operator that you're considering, right?
But eventually you're going to take a look at the individual records. Like if I take a look at the individual records.
So the system will look at subsets of the individual records.
Sorry?
The system will look at subsets of the individual
so,
records.
But
right.
I can, figure out the outliers, not to, it's outlier detection, as you mentioned, is not too hard to do, right?
That's right, that's right.
So the problem that, okay, I figure out these are the records that are causing trouble.
Mm-hmm.
Or is it, figuring that out, or is it figuring out, well, these are the trouble ones, but what can I do? What is the, conjecture that cause these to, to be outlier?
Yeah, so what we want to, you can imagine there's kind of 2 steps that we're trying to solve, right? One is, what are subsets of the input records that would be causing this outlier to occur? And the second is then constructing a predicate to describe them. Right. And so we'd like to basically, so you suggested that, for particular aggregate operators, there are particular, optimizations, right? And so we'll get to how that works. Yeah. But first, in order to do anything, we need to first quantify the influence of a particular predicate or even subset of the results inputs that we care about. Yes?
Can I just cluster all the points based on their distance? Because the outlier must have longer distance than other points.
So that works so that's an optimization that works for particular operators, right? But that, in general, doesn't work. So we've tried versions of these techniques.
Okay.
Yeah. So other versions you can imagine is, well, why don't you use something like PCA to reduce the dimensionality and so on, right? And so those work for specific types of problems. But in general, we'd like to develop a framework that works for arbitrary numerical operators. Okay?
Does the PCA thing work for your example there? Example? The temperature seat.
Which
The room temperature.
let's talk about it offline.
Oh,
I probably won't make it through my talk.
okay.
That's okay, don't worry.
Interesting. So how do we actually quantify the blame for a predicate, right? So if I say, well, I have this predicate sensor equals 3, how much does its sensor readings influence the aggregate result? For example, the average temperature. And so we quantify this using an influence function that's defined over a particular aggregation, and then we apply it for particular predicates. And so I'll just walk you through what this is, starting with the strawman example that just looks at the change in the output. So the user has come to us and said, well, the average temperature is too high. And so what is the score if we consider the predicate sensor equals 3? And here I've labeled in red the records as well as the point that correspond with the sensor readings that match this predicate. So intuitively, if we remove sensor 3's reading, that'll cause a change in the output, right, from the red bar to the black bar. And this, however, itself is not enough because it's underspecified as a scoring function. Because if we consider just sensor equals 3 or 2, then that causes a slightly larger change in the output value. However, we intuitively prefer the previous one because it's a little simpler, right, in terms of the number of records it requires. And so to take into account this problem, we add a regularization term, which divides by the number of records necessary to make this change. So you can think of this as the discrete differential of the output. And then in this case now, we would prefer sensor equals 3 because it requires only one record to make this change. However, the preference, whether or not we like the left one or the right one, is up to the user ultimately. And so we add a final hyperparameter lambda to control for this. So if the user says, I just want the average temperature to be as low as possible, then she would set it to 0, in which case we would prefer the predicate on the right. So that kind of gives you a flavor of the influence score. And so so this is the simplest version, right, which says for a single outlier, why was it too high? And then we've developed additional extensions to support, well, directional comparisons. Why was this result too low? Why was it not an exact value? Supporting multiple outliers as well as multiple normal results that should not be influenced by the predicate. And all of these kind of make this more complex. However, this gives you an intuitive understanding of what we're talking about. And by solving now the influential predicates problem of identifying the predicate that maximizes the score, we can then now say, well, this is the predicate we can most blame. And to give you a sense of what this looks like, let's just construct predicates over the voltage and humidity dimensions. And so here, you can think of each of these points as an individual temperature reading. And the user has said, well, the average temperature across all of these points is too high, in which case you want to place the blame on the orange and red readings, right? So when we run Scorpion with a lambda of 0, we basically construct a predicate over roughly almost the entire data set, because deleting all of them will drive the average temperature down the most. And as we increase lambda, then you can see the predicate we generate contracts to just the high temperature readings, right, which are the ones we care about. And so we've run additional experiments with formal notions of what a predicate's quality is. We've run it on higher dimensional data, different types of data sets, different aggregation operators, and also real world data sets. And the message we get is the influence score is kind of meaningful. However, as we see here, it's sensitive to lambda. And so later on, I'll tell you how we deal with this sensitivity.
Sorry, can you just, the plot is humidity versus voltage, you're plotting the values for each of the data points from the sensors.
Yes, so the
In
temperature
heat map, which
is by
represents
color, yes.
Okay.
So for example, this would be a 10 degree temperature reading, and then this would be 45, this would be 80.
And the point, so each point in this plot is a single sensor.
Is a single sensor.
Okay.
Yeah. It's a single sensor reading.
Reading. Yes, reading,
Yes.
right.
So I really like this a lot, but I'm trying to figure out whether records is the right thing to minimize over, because going back to the thing, I mean, to me, like if I decided a sensor is iffy, I might prefer to just throw that sensor out of the data altogether. That's throwing more records out, you know what I'm saying? Or I might take the assumption that once a sensor starts acting wonky, from then on I'm going to throw it out of the data, even though I might be throwing out some good readings because I think it's become unreliable from that point. And so it's sort of the thing that you're actually throwing out isn't the number, the thing you're quantifying over isn't sort of the number of records, it's something a little bit different than that. It's sort of the number of witnesses or something. I'm not really sure what you call it, but does that make sense?
I understand. What you're saying is sometimes you might want a high lambda, sometimes you might want a low lambda, right? Basically, when you have a low lambda, you're going to match more records because you're less sensitive to the number.
Yeah, but I guess what I'm saying is the records that you're going to match or not match kind of have a particular pattern. Namely, I know that it's around this sensor as opposed to around this reading, for example.
When you say reading, what you're saying is, well, it's roughly around this temperature value, right? In which case, we'll identify the predicate that kind of matches those readings.
We should take this off.
Yeah, let's take it off. Yeah, that's definitely interesting. So the thing is, like, you and I...
Sorry. Let me, one second. I'm wondering, every question that I hear, I'm wondering how much is this being somehow misled by the example, because I keep mapping back to, what I'm having in the back of my head is the cancer one.
Mm-hmm.
I'm throwing a sensor, is throwing a patient, or the whole picture of the patient.
Okay.
And it's like, when I go back to that one, it's like, okay, I'm not sure that I can map it that well.
Okay.
I think that the example is cool because they give you good pictures, but at the same time,
I may have misled you. So in the sensor example, if we were to apply the cancer example, if we were to apply it to Scorpion, which we're currently doing, then the complaint would be, well, I've looked at each of my departments, or I've looked at each of the different cancers, and I've noticed that lung cancer has this spike, right? And so the user then says, well, I want to understand why lung cancer is particularly expensive, and we'll identify, well, it's because of these oncologists. And like, yes.
So I think we are losing sight of stuff because of the sensor example, but I think what you're basically saying is that you have a scientist, they have a bunch of data, they have a hypothesis, their hypothesis has failed, and they want to ask, what is it about my data that's making my hypothesis
That's correct.
fail? Is that what it boils down to?
That's correct.
Okay. So I think that's different from a sensor reading being bad or a particular sensor being bad.
Are we good?
Yeah.
All right, I'm just gonna power on. Okay.
don't worry about it.
So,
Hold the line.
so like you said, like data analysts are already kind of doing this process and answering this question, right? So popular visualization tools like Splunk, Tableau, and even just traditional OLAP Cube technology and databases are designed to make individual steps in this process faster, right? So Splunk makes it easy to look at your expenses, by week, and then say, well, there's an outlier, here in this week. So then, can I drill down by region or by day or by, by some other attribute? And you can see how, while this is like fast, each, step is fast. This entire process still is completely manual, right? And if you have a high-dimensional data, or if you just have multiple outliers, then keeping track of all this information is very difficult for the user. And so, in contrast, we've kind of formalized this entire process and capture it by solving this influential predicates problem. And in addition, these kind of implicit parameters like lambda are explicitly captured as knobs. So then now I'd like to jump into the optimization and systems part of this system. So Scorpion takes as input the original SQL query, a set of outlier and normal results, the lambda parameter, and then a description of how these outliers are wrong. Solves the influential predicates problem in order to compute the optimal predicate. Right? And we split this in the systems view into a search algorithm and a component to compute the influence score for a predicate. And of course, we all know that the naive algorithm that looks through one-dimensional, two-dimensional, three-dimensional predicates, works for all cases. However, it's going to be very, very slow. Right? So on a simple two-dimensional data set, depending on how you discretize it, it takes over 300 seconds to encounter the optimal predicate. And so this is because of both the search space as well as the fact that computing the influence can be quite expensive as well. And so our main insight in this work is to identify a taxonomy of popular aggregation operators, and then for different properties, identify optimizations. And so this is where things like what you two suggested would fit into the system. So some of the optimizations I'll just talk about include making the influence computation faster. So the naive way to do it, if we're computing the sum over 1, 2, 3, 4, 5, and we want to know, well, what's the influence of the predicate that matches 4 and 5, what we need to do is first remove 4 and 5 from the input data, and then recompute the sum again, in order to compute the new result value, right? And of course, you can imagine if we have 1 million input readings, then this would be quite expensive, particularly because the predicate usually matches a small number of records. So the incrementally removable property, such as sum, allows us to recompute this result directly. So here, in this case, we just subtract 4 and 5 from the original result, and we get 6. Right? So this is something that we all kind of understand, and it works for operators such as average, standard deviation, count, sum, as well as linear regression and Pearson correlation, higher moments of centrality. On the other side, we've developed top-down and bottom-up algorithms based on the independent and monotonic properties that work for average, standard deviation, and count, sum. And so for the sake of time, I'll just talk about how the independent property allows us to develop a top-down algorithm for operators such as average. Yes?
I'm sorry, is incremental removal the same as linear?
It depends on what you mean by the linear.
I guess you're right.
Yeah. Yeah.
It looked kind of linear to me.
It's very similar to other notions. Let's talk about offline. I want to at least make it through this part of the talk. So the requirements for independent operators of property is that first, each reading independently influences the result, right? So average is like this. And in addition, the aggregate operator is a normalized statistic, meaning if all of the temperature readings were at 50, then it doesn't matter if we have one reading or 100 of them. The average is still the same, right? And because of these two properties, if the user says the average is too high, we know two things. The first is that if the individual temperature reading is higher, then so is its individual influence on the average temperature. The second thing we know is that clusters of similar temperature readings have the same, roughly the same influence as any of the individual ones within that cluster. And what this suggests is along this temperature dimension, we just want to identify splits to just identify clusters of similar temperature readings, right? And so the top-down algorithm essentially does this, however, not on temperature, which is what we're aggregating over, but on the other attributes. And so algorithm is essentially just a regression tree, partitioning in order to basically split the space into partitions of similar temperature readings. So for example, we would start with axis parallel splits, such as a vertical or horizontal split, and then we would choose the vertical one because it reduces the standard deviation the most. And so we deal with discrete attributes in this case by just taking the range and then splitting it into buckets. For example, if we have sensors 1 through 10, then we split it into buckets of 1 through 5 and 6 through 10. Right? So this is how we deal with that nasty problem of discrete attributes. And so we would just continue on and keep splitting until the standard deviation within each of these clusters is below some threshold. And the main intuition for optimization here is that we can avoid completely splitting this part because it doesn't contain anything that's influential to begin with, right? So we can avoid over-partitioning the space. So now, now we have a partitioning, and then we use a merging phase to then merge adjacent partitions in order to construct the optimal predicate. In this case, for example, we would start with this one, merge it with its adjacent neighbor, merge it again, and then the influence doesn't increase any further, so we would then stop. And the way we deal with discrete attributes in this case is we only allow them to be candidates for merging if their continuous ranges are similar. For example, if I consider whether or not to merge sensor 1 and sensor 2, I'll only do so if the voltage ranges are roughly similar. And this lets us run Scorpion in tractable amounts of time. As the demo kind of showed you, it kind of runs in reasonable amounts of time. So here we're capping a naive algorithm at 1 hour. And I'm showing you along the y-axis the cost in seconds on log scale. And on the x-axis, just the number of records per hour. So we're varying from 1,000 to 10,000. And so the independent property, along with the monotonic property I didn't tell you about earlier, allows us to develop these kind of heuristics for the 4 major database aggregation operators we care about. So the last part in this section is dealing with this hyperparameter, lambda, right? As we saw, the types of results we generate is sensitive to this value. And so you might wonder, well, can we just identify the optimal value using something like cross-validation? And the reason we can't is twofold. First, we don't have some training set to run cross-validation over. And secondly, it depends on user preference, right? So instead, we want to find efficient ways to sweep through this parameter space. And for this, we've developed 2 caching opportunities to do so. The first is that the top-down partitioning runs independent of lambda, so we can just avoid the cost in the future. And secondly, if we're reducing lambda, we can also use previous results for the merging phase. And to see how this works, let's say this was the previous result. if the user decreases lambda, she's saying, I'm willing to accept more sensor readings within my predicate, so we can just start from there during the merging phase, reduce it, start from there. And this lets us get up to 25x performance improvements when we're just varying this lambda parameter. And we're also we're pretty close to kind of single pass algorithms for just a continuous range of lambda values. And so I was coding that up this morning. The contributions in our work then is that we've developed one of the first systems to help explain outliers in aggregation query results. And to do this, we've developed a general framework that works for a large class of why questions and aggregation operators. And we've developed optimizations that are based on operator properties rather than for specific use cases. And by using something like Scorpion, you can imagine making things like data cleaning easier, as well as cost analysis problems such as the lung cancer problem or Obama's expenditure problems. So Scorpion uses a relatively simple pipeline in terms of computing the results, right? We just group by some set of attributes, and we compute a statistic. And the first thing we need to do in order to run Scorpion is to go back from what we highlighted in the results to the subset of the input that generated them. In general, however, this is a difficult problem if we have workflows that contain black box operators or custom code, right? And so Sub-Zero is then a system to help us manage this process for these more complicated scenarios. And so this tracing back from the results back to the inputs is called lineage tracing in database terms. And so Sub-Zero is a high-performance lineage system. And the example I use throughout this part is based on our collaborators at LSST, which is the Large Synaptic Survey Telescope. And so basically, you can imagine what their pipeline is, right? They take a big image, they clean it up, and they detect stars. And they're expecting to be processing over 300,000 images per night, or 10 million images a month. And you can imagine, so one of the things they want to do is, as they detect new stars, be able to ask, well, what's up with that star, right? Is this, due to a speck of, a random speck of light, or is this actually a star that we can use in some way? In order to understand this, they need to first trace back to the pixels that were used to compute this star. And if it turns out that they're faulty in some way, they need some way of discounting all of the other results that depend on these pixels. In order to do this, it's actually quite complex because the pipeline is quite complex. In addition to matrix operations to remove atmospheric noise, fix lens distortions, and so on, there's also these custom operators to deal with cosmic rays. So these are high energy particles from outer space that, for laptops, they cause memory errors, but for telescopes, they look identical to stars. And the way they deal with this is by taking two pictures of the same portion of the sky and then writing this custom code in order to detect these cosmic rays in the images, merge them, remove the cosmic rays, and then finally detect the stars. And you can imagine each of these operators takes a giant image as input, generates a giant image as output, and they want to know pixel level relationships, right? And so we need some system that allows the developer to efficiently expose this information and be able to manage the cost of doing so. So in existing work, most lineage systems fall into two categories. Coarse-grained systems track this information at the file or database table level, right? And this incurs low overhead. However, they can't answer these types of pixel-level queries. On the other hand, the fine-grained systems can answer these queries. However, they have extremely high amounts of overhead because they're storing essentially an input for every pixel result. And there's solutions for SQL operators. However, in general, there's no system to do this. And so let's just build out such a lineage system for LSST. The first thing we would do is we would instrument one of our operators to just generate this information, right? These pixel level relationships, index them, so then when the user asks, well, can I trace back from that star all the way back to the inputs and get the pixels, they can take that star, look up in the index, and identify the coordinates of the inputs that generated that star. And then recursively apply this procedure all the way until they get back the pixels from the original image. Of course, to do this, we would then need to instrument every single one of our operators in order to output this information, right? So this is clearly not scalable to the data sizes nor to the complexity of the workflows. And so in our work, we've developed a more efficient way to represent this lineage information that's both simple as well as effective for these scientific applications. And then I'll tell you how we make these trade-offs between generating and indexing this information versus this tracing performance. And then finally, some design techniques that we need to use for these modern lineage systems. And since we're kind of running out of time, I'll just give you kind of a flavor of what's going on. So the first is, we've developed this payload encoding technique. And the main way it works is, think of matrix multiply, right? So matrix multiply, we know that for this coordinate x, it depends on this column and this row. And so rather than explicitly storing any information, we can just define a mapping function that takes x's coordinate and just computes its lineage, because we know the semantics of how matrix multiply works. However, for general operators, we don't have this ability. And it turns out that there's kind of a good middle ground between explicitly storing this information, these pointer informations, and this mapping function that we've defined as payload lineage. So I'll just tell you how this works. Find stars looks for clusters of bright pixels and labels the center as a star. And the semantics are, if there's no star in the output pixel, then it just depends on the corresponding pixel. Otherwise, it depends on a neighborhood whose radius is dynamically determined, right? So payload lineage allows the developer to, in addition to each output pixel, also store some binary blob of information, in this case, the radius. Now they have an ability to implement a mapping function that's more efficient. And the nice thing with this is most scientific applications are sparse, so we can avoid storing anything at all for all of the pixels that don't contain stars, because you can just interpret a null binary blob as just a radius of 0, right? And so by doing this, we're able to first define mapping functions for all of these guys, implement pointer and payload lineage for the black box operators, and we also have the additional ability to just not store anything at all, because we can always recompute this lineage at runtime. And so by doing so, I'll just show you. Basically, when compared against existing techniques, we do significantly better in terms of disk and runtime slowdowns. So basically, when I run the LSSD pipeline, how much do I slow it down, and how much disk storage space do I need in order to store this lineage information? And so in comparison, payload lineage does extremely well compared to the pointer-based approaches, and we get significant query performance improvements. Of course, payload lineage is not always available to us. And so it's nice that we have multiple implementations for writing out lineage information, because this is analogous to a database system where for the same logical operator, we have multiple physical implementations. And by doing so, we can leverage existing cost-based optimizer techniques to span between the two existing extreme designs in order to identify, on an operator-by-operator basis, what's the optimal strategy, right, in terms of what lineage to generate and how to index it. And so we just encode this as an integer linear programming formulation. Basically, we're trying to minimize the expected cost of executing lineage queries subject to constraints for the disk and runtime overhead. And this basically is just varying the storage constraint from 10 to 100 megabytes given to the optimizer. And the main message is, look, as you give us more space, we're going to take up more space, but we'll also decrease the query runtimes. So it's kind of what you would expect, because otherwise I wouldn't be showing you this graph. However, also the message is the optimizer is necessary if you're building out these systems. Because as we've seen earlier, the difference between a poor strategy and a good one can be hundreds or thousands of times different in terms of all three of the metrics we care about, right? The storage cost, the runtime slowdown, and query performance. And so we need such an optimizer because the optimal strategy depends on a huge number of different factors. And so Sub-Zero is the first fine-grained lineage system that can allow the developer to make these trade-offs between the cost of storing these auxiliary data structures and the lineage query performance. And our techniques are being implemented in SciDB that I think Jenny probably told you about last week. And so SciDB is being used by astronomers, environmental scientists, and genomists, and other science domains. So I don't think I can get to my. So I'll just finish up. Okay. So earlier on in this talk, I told you there's this need to close the loop between the results and the inputs. And so I've told you about two systems, Scorpion and Sub-Zero, that help close the loop. And although they're sworn enemies in Mortal Kombat, which is a video game I copied these characters from, they can actually work together to help data users, right? Because by first tracking outliers back to their inputs and then constructing predicates over the ones we want to place the blame on. And of course, there's many other ways that we can help the data users. And due to lack, how much time do I have?
Another 5 minutes.
Another 5 minutes. Yeah, I'm fine. Okay.
It's a soft bet.
At least 10 minutes.
Oh, okay, okay. So there are, of course, other ways that we can help data users, right? And so one way that I think would be interesting is to look at the result side. And so how do we actually visualize and construct visual representations of the results? And this is and then it's interesting to think about how much can we integrate the database management system with the visualization system. And this is because in existing architectures, these two are connected via just a SQL interface. And the downside to this, although it's an elegant, like systems-wise, is that the visualization ends up re-implementing a lot of the database techniques that we care about. In fact, there are some visualization systems that just implement their own database inside of itself, right? So there's a lot of, there's a lot of unnecessary systems work in the visualization layer. In the database side, we also have a lack of semantics for doing optimizations across the entire stack. And this is bad because the main trick that database people play is by understanding semantics of the operators, we can then exploit them in some way, right? And so if we can somehow kind of encapsulate the visualization level semantics into the data management system, then we should be able to get, better performance, faster development for creating visualizations, as well as more powerful visualization features. And so some of the benefits from the database optimization side include using perceptual inaccuracies to tell us, what kinds of approximation games we can play. For example, either sampling or aggregating data. By having access to both the data statistics, the query workload, as well as the visualization outputs, then we have a better understanding across the entire stack what features might be valuable for recommending other views to the data user. By understanding things like occlusion, the fact that one piece of data is occluded behind another piece, then that can directly inform us the types of filtering we might want to do in the query processing pipeline to avoid computing results that we're not going to see anyways, right? And then finally, understanding the semantics of how interactions work will give the database better understandings of how to do things like prefetching and pre-computation. And of course, I've been playing around with some of these ideas, and the visualization side gets benefits as well. For example, as we extend database systems with the ability to explain outliers, then visualization systems get this for free, right? And so the demo I showed you uses a declarative visualization system that I've been playing around with that I've built. And it just takes a couple lines of extra code in order to add the Scorpion functionality into place. And similarly, we can get a lot of benefit from extending databases to support lineage as well. And so one type of thing you might imagine is an interaction. So here, this is just the visualization system I built, and I'm just plotting some random data. Okay, so don't worry about what it means. There's just 3 views of the data. And one of the popular interaction techniques that's quite difficult to get right is essentially brushing and linking. So when I highlight some data here, the corresponding data in this view and that other view that share the same inputs are also highlighted. And as you can see, this is naturally expressed as a lineage query because we're going from the output, tracing back to the inputs, and then tracing forward to all the other subsequent output results, right? And by expressing this as such, it only took me 3 lines of additional code to just execute these lineage queries in order to construct this interaction. And by expressing it in such a way, then the database can do the job of scaling and making sure the latency is below some threshold. And so now it becomes an optimization problem. Of course, there's also interesting work in terms of other ways to close the loop. So in the Scorpion work, I described subsets of the data that may be causing outliers. And similarly, you can imagine identifying subsets of the historical query transactions that might be to blame. So as a concrete example, I've been talking to the chief scientist of Verizon, and he was telling me, a while ago, they started getting a lot of complaints in their call center from customers in Kansas that their billing was too high. And ultimately, it turned out the reason was because the tax code in Kansas had changed, and so the query that updated this information in the database got the tax code, the tax rate wrong. And so you can imagine this affects everyone in Kansas, right? And so if we can use some samples of complaints of the current state of the database system to identify, what are possible historical transactions that have a greater implications in the current state, then Verizon could have avoided a lot of these complaints. So you can imagine this is another form of kind of outlier explanation. So in closing the loop on data analysis, I've told you about a couple projects I've worked on in the past and hope to continue working on in the future that target different points in the data analysis pipeline. And hopefully, you leave with this idea that it's valuable to consider not just raw number crunching, but other parts of this process when building out these next generation data processing systems. And of course, I couldn't have done this without a huge number of past and current collaborators, advisors, and friends. And so I'd like to thank all of them. You've been a great audience, and it's been pretty fun telling you about these projects I've worked on.
So I have a question about the outlier explanation work. So it seems that the key of your technique is try to solve the space exploration problem, right?
Yeah.
And it's not very clear to me, like, you have 3 techniques, some like independent and another couple. Are you able to bound the amount of search in terms of like linear to the dimension or the number of sense, what are the, do you have any
Or are there hard bounds on this?
Or, because you're talking about general framework, right?
That's right. Are there hard bounds to this? Well, you can imagine even in this partitioning case. So first of all, they're all heuristics. And the reason why is because even in the partitioning case, we could end up in a degenerate scenario of just creating partitions for every input value, right? So in that case, it becomes, essentially, like we can't control that. So the way we can do that is by either aggressively relaxing this thresholding for the stopping criteria, or by just constraining the amount of time it takes. So one nice property of like these algorithms is like you can stop at any point, and it gives you the best result that it's gotten so far. But
yeah, but
we
not necessarily.
I don't think we can say anything about bounding it.
Yeah. So, but even given let's say 1 day time, it itself doesn't automatically adjust to the complexity to give you the best result it can achieve in 1 day, right? So my concern, you may have to manually tune the parameter here and there, and to run the experiments over and over again, try to get the best result.
Okay. So I think, yeah, a good direction to think about, I think, is interesting, is like, given a time constraint, like how do we fudge with the parameters to get the best results? Yeah, I think that's a good point. Yeah.
Do you know how you select the predicates in Scorpion? Does Scorpion select the predicates, or does the user?
Yeah, so Scorpion, basically, we formulate it as this optimization problem, right? Where for a particular predicate, we want to identify the predicate with the highest influence score. And so Scorpion then searches through the predicate space to identify the predicate that is most responsible.
But isn't it too expensive to go through all data?
That's right. And so the properties I described kind of help us develop heuristics for searching through this space. So yeah, like you said, this is an exponential space, so we clearly can't search all of it.
Even combinations of predicates too, or just it's like all combinations of the overall scheme?
Do I search through all combinations of predicates? No, the goal is to not do that. The goal is to avoid searching through like classes of predicates where they're not going to matter. Yeah. And so that's basically the problem we try to tackle, is how to do that.
The user in the loop, I'm wondering, with the user in the loop, I'm wondering if you guys have done, this might not be your work, but I'm wondering if your group has done like user studies to evaluate whether these target scientists can understand and apply these systems to their domain problems.
Right. So what I'm currently working on right now is we're working with Jim Michelson. So we've gotten through the IRB process, and so now we're going through the process of, here's where, here's what Scorpion kind of returns, and is it something you get useful? So we're basically on the steps.
You're getting ready to do a user study.
That's right.
Okay.
Yeah. It'll be interesting.
Yeah,
I mean,
absolutely.
So, 2 questions again about the outlier detection and explanation. So, first, so in the influence score, what you're measuring there in the numerator is change. So if that seems like actually the only change you care about is actually a change back to normalcy.
Directional, yeah. So that's the extension for directional change. And so in reality, what we express when the user expresses this error, it's encoded as an error vector. And so the goal is to basically move along this error vector as much as we can.
Okay, but even if you go past the sort of...
So if you go past it, then the score starts decreasing.
Okay. Okay, and then the other thing is, in the examples you showed us, you were only looking at like rectangles in that kind of feature space.
That's right.
Did you have those kinds of constraints on the sort of simplicity of the predicate?
What do you mean by simplicity?
Well, I mean, so you could, one way to crank up that influence score would be maybe to produce a really complicated predicate, right? That sort of really subselects a small number of points. But it might be sort of really painful to look at and
So,
wouldn't give you insight.
Yes, so what you're suggesting actually is, why don't we deal with something like disjunctions, right? Because once you support disjunctions, then like the space then blows up even more, in which case like this complexity comes into play. When we're just dealing with a single conjunction of a single predicate, then we would have the problem of, well, this is too precise, but that just means the lambda value is high. So you see how this would...
I mean, if the feature space is really large, I think you get really, you could start adding in conjunctions where you're only throwing out individual examples, right?
I think so. So I mean, there's simple extensions to this to kind of take that into account. For example, you can just also penalize like the complexity of the predicate. We haven't used that. I think that would be interesting. Yeah. Actually, so originally I tried doing that. So some of the features I tried include like the complexity of the predicate, the length of the predicate string, this thing that I told you about today. The thing that's been most effective has been just the number of records. And what we end up doing actually is when we search the space, we get a lot of redundant predicates that all match the same subset of the data. And so in reality, what we do is this like kind of clustering thing at the end that kind of clusters together predicates that like do the same thing. And so in that case, we then end up picking the predicate that has the smallest string length or simplicity. And that's been pretty effective.
All right. Thank you, speaker.